Hello everybody! I hope everyone's having a wonderful day. So we're going to be picking up from where we left off last time. I'm going to be talking more about how logarithms and big O notation tend to relate to each other. So I'm going to be covering a few different properties that logarithms have when we talk about asymptotic notation. So the first one I want to talk about, and this relates to my previous video where I was talking about the power rule of logarithms. We're going to see how that plays out. What I'm going to be doing is I'm going to be trying to prove for you that if I have log base b of n to the k, where n to the k is a term inside the logarithmic function, that this is big O of log base b of n. So the big thing I want you to notice is that this k here is just, it's irrelevant. That's the first thing I want to point out, is that single exponents, where that exponent is in fact a constant, are not relevant. You're going to see as we do the proof that they're just going to turn into a multiplicative constant. You're going to find that logarithms have this nice property, and we're going to try pushing it to an extreme in this video. And then we'll move on to a couple of other properties that logarithms have. So what are we going to do? We're going to try proving this, because it's easy enough just for me to explain that idea to you. I have to actually prove it. That's kind of how we do mathematical stuff. So what's the game plan? I'm just going to give you the definition of big O. I'm going to say that, what I'm going to do with that, and then we're going to proceed from there. That's going to be the strategy. So what do I normally do? I say, so remember, what's the definition of big O again? We have to find two constants. One's a positive real number, one's a positive integer. Such that, so I'm going to we find constants, c, which is a positive real number, and n0, which is a positive integer. Positive integer. I was about to put a 0 there. It's a plus. Positive integer, such that what? Such that what? Such that log base b of n to the k is less than or equal to c times log base b of n. And is this just something just generally true, or do I have to have a quantifier? I have to have a quantifier. I can't just state this blindly. What's n0's function? It has to be for all n greater or equal to n0. So remember, we have to find some point or on where that inequality is always going to hold. So what are we going to do? Here's the trick. So this is where I want you to come back to the thing I just explained to you previously. And this comes down to the power rule of logarithms. Imagine if I pretended this big O wasn't here. Imagine if I wanted to write this again. Just imagine I wrote this left part. You would agree with me that this should be equal to k times log base b of n if you remember the power rule of logarithms. Remember, k is a constant. So how can I make it so that this inequality is going to work no matter what n is for all positive integers? Well, maybe I should make c equal to k, and you invoke the power rule. That's what we're going to do. So I'm going to pick c is equal to k. Then we find constant n0 such that for all n greater or equal to n0, log base b of n to the k is less than or equal to k times log base b of n. Right? That's what we're going to do next. So now this is where I'm going to invoke the power rule of logarithms. So remember, the whole idea is that you can take this exponent, you can drop it out in front. So by the power rule of logarithms, by the power rule of logarithms, we know that log base b of n to the k is equal to k times log base b of n for all n greater or equal to 1. So choose. So what should I choose for n0 then? N0 is equal to 1. I can pick 2, pick 3. It doesn't matter as long as I pick the smallest possible one. The smallest possible one I could use is 1. At least to satisfy this equality. Now, do you see why this implies that? Well, remember, this literally says that these are equal to one another. So the inequality must hold. Therefore, by the definition of big O, log base b of n to the k is big O of log base b of n. And we're done. Piece of cake. So all I did was I used the power rule of logarithms, which we proved last time. So you might ask, Dan, can we push this any further? Can we generalize this idea any further than we currently have? Yes. Yes, in fact, you might ask, okay, well, what can the constant actually be? Because remember, k is in fact some fixed number. So how far can I really push this? Well, I'm going to show you just an example of how much you can push the needle a little further. I like to usually put this one on assignments for students, just to illustrate this point, but seeing as this is a nice resource, I feel like I'll put it here. So what we're going to do next is I'm going to prove that the sum from I is equal to 1 to k of log base b of n to the I is big O of log base b of n. So what I'm arguing for you is, unlike before where I just had a single exponential term inside of a logarithm, now I have a whole series. So now I'm going to be so if you're not familiar with that sigma notation over there, what I'm saying is that log base b of n to the 1 plus log base b of n squared plus all the way up to log base b of n to the k, all of this is big O of log base b of n. So I'm going to be pushing this to its extreme, okay? Now, this isn't, you probably could find some obscure way of going even further than this, but I just wanted to illustrate how exponentials behave inside of logarithmic terms. That's the point of this exercise. So let's prove this. I'm going to employ the same strategy I did before, but I might need a different constant to make this work. So what's the first thing I do? I write down what the game plan is. Let us find constants c and n0, which, what is n0 again? It's a positive integer. Such that what? The sum of log base b of n to the I, where I sum from I is equal to 1 to k, is in fact less than or equal to c times log base b of n. For all what? For all n greater or equal to n0. So you might ask, Dan, what should I pick for the constant? Now I'm going to give you the intuition up front, and then we're going to see how this works. Okay, you'd agree with me that this exponent here, this 1, by the power rule, this should go right here, right? So I have 1 times log base b of n. This 2, by the power rule, it would be 2 times log base b of n. If I had a cube term inside of a logarithm, that would become 3 times log base b of n. So what I'm going to do is I'm going to pick a constant that's going to match that. Now remember, k is fixed. It is not variable. You can fix it any way you like. So I'm going to pick c to be matching that idea. I'm going to pick c is equal to 1 plus 2 plus 3 all the way up to plus k. Now, if you're handy with your summations, you know that this is looking like this. So it's just the sum from I is equal to 1 to k of I. And you might recognize this series here, this finite series. This is the arithmetic series, which this actually has a closed form expression. That means I give you a very simple formula that evaluates this sum. Just to keep it simple. It equals this. Maybe in the future I'll write out an induction proof for you, just convincing you of this fact. So do you see this is a more complicated concept, but it's indeed a constant, right? Because k is fixed. Then we find n0. Such that for all n greater or equal to n0, the sum from I is equal to 1 of k of log base b of n to the I is less than or equal to k times k plus 1 all over 2 times log base b of n. Now, this is where I'm going to use my intuition I gave you earlier. So now I've picked a constant, and the idea is that this constant is going to capture each one of the logarithmic terms so I can pair them up with the left-hand side. Just like I did over in the previous example, except to the extreme. So for all n greater or equal to 1, observe by the power rule of logarithms the following. The sum from I is equal to 1 to k of log base b of n to the I is going to be equal to what? What's inside of this sum here? What's this equal to? Well, I can pull the I down in front of the logarithmic term, right? So I'm going to write it that way by the power rule. So I have I times log base b of n. Now the next thing you want to notice is that, is this term dependent at all on I? Is it at all? It isn't. So if I took each one of these terms that are based and dependent on I can multiply each one by log base b of n. So I could just take this term, pull it outside of the summation, and then we can proceed. So what I'm going to do is I'm going to write that sum now, which is just I. So that just has I there. And I'm going to multiply it by log base b of n. Because remember, as I add up each one of these terms, all I'm really doing is multiplying it by log base b of n, like I mentioned previously up here when I talked about the power rule. But what's this equal to? Well, I just told you what this sum is. It's k times k plus 1 all over 2 times log base b of n. Wonderful. What does that mean, though? Which equals the right-hand side of the inequality. So what am I going to pick for n0 now then? Well, I told you, this statement is true for all n greater or equal to 1. So I'm going to pick, I usually say select or choose just to keep it a little different from here, but I'll just, for an exemption, I'll pick n0 is equal to 1. Therefore, by selecting such C and n0, it follows from the definition of big O that what? That my statement is true. The sum from I is equal to 1 to k of log base b of n to the I is big O of log base b of n. And we're done. Isn't that fascinating? So now you can see how you can add up logarithmic terms, each one with its own exponent in it, and you still get a logarithmic term without a power involved. Now, a question I have for you is if I change that k to an n, so it's dependent on the input n, will that change the result? I want you to think about that. We're going to try proving the following. So now remember, the upper limit of my summation is not a constant anymore. Now it's n. Now, I want you to think about this. What was the trick I used here in this proof over here, my previous example? That I could find the constant, and that constant was entirely dependent on k. That was the trick that I used. Unfortunately, I can't use that trick anymore here. Now, before I really say what we're trying to prove here, I'm going to first just start off by trying to use the same strategy again. Then we'll see what I'm actually going to be trying to prove. I don't want to spoil the surprise. But the big thing I want you to notice is that I can't do the same trick again when it's actually n in the upper limit of the summation. This isn't k, it's n now. So let's see what happens. So what do I usually do? I usually say we find constants. We find constants c, which is a positive real number, and n0, which is a positive integer, such that for all n greater or equal to n0, the sum from I is equal to 1 to n of log base b of n to the I is less than or equal to c times log. Now I just need to be very careful here. I don't want to spoil this quite yet. Let me go a little ahead here before I say what I'm actually going to prove. I want to go back to the line that I used over here. I want you to see what we're going to do here. I want us to go back to this line over here. And then you're going to see very quickly what I'm going to try to prove for you. And I can't prove it's a logarithmic term just like I had before. It's going to actually depend a little bit more on n this time. I want to revisit something over here. So like I said, this depends on k being a constant. So what did this look like over here? I had it where I used the power rule here, and then what I did was I isolated out all of this. Do you see how this is a k here, and that's how I end up getting that closed form sum? Now, if I put, instead of putting k there, I put n there, would you agree with me that now I have something that isn't going to be a constant times log base b of n? What would that look like? So imagine the k like a banana, and I replace a banana with an apple. So this would be the sum from I is equal to 1 to banana of I. But now, and before, it would be banana times banana plus 1 over 2. If I put an apple there now, it would be the sum from I is equal to 1 to apple of I times log base b of n, which would be apple times apple plus 1 over 2 times log base b of n, right? So now it is changed. Is it a constant there anymore? No. In fact, it's a quadratic term now. Well, it's a quadratic, to be a bit more precise. So, does that give you an idea of what we should actually have there? So it should be something that is like n squared times log base b of n. And that's what we're going to actually prove. So let's go back over here and let's see what we're going to do with this. So that's what I'm going to be actually proving for you. It's not log base b of n, it is n squared times log base b of n in terms of big O here. So that's going to be our goal now. So you might ask, okay, well, what do we do? Now, you remember my previous proof. Now I have all that n squared business sitting out front when I derive the closed form sum. Do I need any constant that's really big? No, I can just pick c is equal to 1. And then I could just use the exact same standard argument that I just used over there. Okay, pick c is equal to 1. Then we identify n0 so that what? So that the sum from I is equal to 1 to n of log base b of n to the I is less than or equal to n squared log base b of n for all n greater or equal to n0, right? So what are we going to do? We're going to apply the power rule of logarithms just like we did before, which is just the theme of this. So I'm going to apply the power rule of logarithms. Then starting on the left-hand side, of the inequality, I'm going to start off on the left-hand side of the inequality. Now, we're going to just use the same strategy we just did previously. I'm going to use the power rule right here. Then what I'm going to do, I'm going to split by just pulling this log base b of n out of the summation, because every term depends on that one being multiplied, but it doesn't actually depend on n. Sorry, I. Remember, read your sums carefully. We're talking about I here. It's that dreaded M word, the mayonnaise. Could do that. And you'd get I time, like the sum with I, you do the exact same strategy there. I'm going to save you a little bit of an extra step here, because you would agree with me that I is in fact, it's in fact, like it can't exceed n, right? So I'm going to do something a little looser with my analysis. I'm going to make an inequality right here. So you can do the exact same strategy we just did before, where I put I in here, and then I use the closed form, and then you'd find out, oh yeah, it is something that you could find another constant, but you'll realize very quickly that you're going to need you might have to do a little bit more work. I want to keep this nice and slick and simple. So I'm going to make the analysis a little smoother here. Not in a precise way, but I mean it keeps things simpler. You'd agree with me that each one of these terms is in fact less than or equal to n, right? So I can write this as n times log base b of n, correct? But what is this? If I add this n times, what should this be? What should this be? You see why this is going to be nice and slick. This is going to be n times log base b of n. But how many times? It's going to be n times. So it's going to be n squared. So because that's n times times log base b of n. So this is, in fact, the right-hand side of our inequality. So what am I going to pick for n0 then? I can choose n0 is equal to 1. Thus, by the definition of big O, the sum from I is equal to 1 to n of log base b of n to the I is big O of n squared log base b of n. And we're done. End of proof. Wonderful. So do you see how in this case, because now the exponent depends on n, that we cannot obtain the nice, just simple logarithmic term we had in the big O like before? So I encourage you to try this by swapping out what I just did in this step and try it with the other way that I did it in the previous example by replacing k with n. Try that out and see if you can make any difference. Just you want to convince yourself that in fact this is in fact true. This is in fact a true statement, but I want to see if you can do any better by in fact tightening this a little bit by using the I here and using a closed form sum. That's what I want you to try, okay? So this shows you enough things that you can do with the power rule of logarithms. This just shows you that in a logarithm, if you have a logarithmic term with an exponent, a single exponent inside there, it can be irrelevant if in fact even it can be irrelevant if it's a constant. That's the big message here. Is that interesting?